cool lecture. I'm excited to give this lecture. It's too bad that I'm not actually able to be in St. John's to participate with you guys. In the previous class, we learned about exponential growth, and I'm sure you've heard of that before in ecology, biology, even in high school. You probably covered the topic of exponential growth. Now what I want to do is try and apply the idea to a real life example. And so one of the examples that is often given in textbooks for exponential growth is the introduction of pheasants to Protection Island. And you can actually go back and get the thesis that contains the data for the growth of the pheasant population. So on the left you see a male pheasant. He's looking quite charismatic, and on the right you've got the hen. So there's sexual dimorphism there. Let's just look at the So we got the male there. He's vocalizing. Okay, so that was just to put a face to the name, and so we know the organism that we're thinking about here. So ring-necked pheasants on Protection Island, and that's an island that's off the coast of Washington State in the United States. So the thesis that I got this data from is he got his master's degree published in 1940, or published as a thesis in 1940. And there's some really cool figures in here. One is this hand-drawn map of the island showing some of the different habitat. So we've got grassland and dunes, some woods. Here's some other figures from the thesis. Again, it was completed in 1940, so we've got some black and white pictures. One of an owl that's killed a young female pheasant, and another one of a pheasant that's eating potatoes. Okay, this is some of the information that I was able to take from the thesis that we can use to estimate the quantities of interest in the exponential growth formula. So I'm just going to skip forward and tell you the questions that you'll need to answer. So ideally the census points should be exactly 1 year apart. I want you to tell me, when does the census occur on Protection Island? So that's when is the population measured, and how does this relate to the biology of the pheasant? And question 2, what are the values of N0, N1, and N2, where N0 is the initial population size, and NT is the size of the population T years after the time of the first census? So I'll have Mr. Fofana write these questions on the board, and here's the information that you can use. In May 1939, there were 10 pheasants that were introduced to the island. Before the next breeding season, there were 35. On November 1938, a census estimated that there were 110 pheasants. On October 13, 1939, a census estimated that there were 400 pheasants, and pheasant chicks are born during the summer. So remember that this is a population in the Northern Hemisphere. So take out a sheet of paper and try and answer these questions that I have on the next slide that have been written on the board, and we'll just stay on the slide while you're doing that. You can have about 5 minutes to answer those questions. So now we can unpause the video. One thing that I wanted to say about this is, so over here I say ideally the census points should be exactly a year apart, and you can see that they're not, because we start with 10 pheasants and that number is given in May, and then there's no census that occurs in November, October of 1937. So we just assume that the census for October-November 1937 is 35. And we assume also that there was no change in the number of pheasants between November-October 1936 and the time at which the pheasants were introduced, so May 1937. So I guess we're assuming that if they had been introduced earlier, there would still be 10 pheasants in May if they were introduced in October, November. So you see, working with real information, it's not quite as perfect as what the equations would like you would like them to be, but I don't think it's not too terrible anything that has gone on here. It's probably, given the biology of the pheasants, roughly the numbers that we're assuming for 1937 and 1936 are probably pretty close to what they would actually have been. So let's just do a quick recall about what the population equation looks like for exponential growth. So we have the number of individuals in the next year is equal to the number of individuals this year plus the number of births minus the number of deaths. And because you have all these n of t's, you can factor out a lambda and just define lambda to be 1 plus b minus d. So that's just doing a bit of factoring. So in this equation we have d, which is the fraction of the population that dies each year, and this is what we want to estimate now. From the thesis, you can see, or it's reported that between 1938 and 1939, between the censuses, the researcher Ross Newcomb observed that 17 out of 110 adult birds died. So the third question I want you to answer is, D is the fraction of the population that dies each year. What is D for the ring-tailed pheasant population on Protection Island? So I'm just going to have Mr. Fofana pause the video here, and you can add that answer to the sheet of paper that you've been working on. So now that we've unpaused the video, one comment that I would have is that this thesis only provides information on the survivorship between 1938 and 1939. But had there been information for additional time periods, we could calculate D for each of the year periods that we have and then take the mean of that, and that would be a better, more robust estimate of what D is. So those questions that you answered had pretty clear answers. The information on reproduction is a lot more difficult to mold into the shape of the, or it's not more difficult, it's just a bit trickier to mold into the information that you need in order to estimate the birth rate. Okay, here's some of the information that's given in the thesis, and not all of this is going to be relevant. You need to think about which is relevant to estimating B and which is not. So just skip ahead to the questions here. Again, I'll have Mr. Fofana write these on the board while you guys are thinking about the information that's given in the thesis. So B is the per capita number of births per year, and that's unitless. We've already estimated D, and we know that there's just a simple formula for calculating lambda, the finite rate of population growth. So the two questions that you need to answer are, what's the value of B and what's the value of lambda? The information given in the thesis about reproduction is that during the 1938 nesting season, there were 5.86 eggs per nest, and 83.57% of the eggs hatched. During the 1939 nesting season, there were more eggs per nest, 8.73, but fewer of them hatched, 64.58% hatched, and the average number of chicks per clutch was 6.93. And you also want to assume that the sex ratio is 50 to 50 male to female. So we'll pause the presentation here and think about this information and how it relates to trying to estimate what B is. And again, this is kind of tricky and you need to think a bit carefully, I think. So we'll unpause the video and look at the answers. So for B, we take the average number of chicks per clutch and divide it by 2. Does anyone know why we would divide it by 2? So the reason for dividing by 2 is it's a birth rate, or this is a per capita number of births. So it's for every individual in the population. And we're assuming a 50-50 sex ratio. So that number of chicks is for male and female couple. So we need to divide the number of chicks by the number of parents, which is 2, so that we get a reproductive rate that is per individual in the population. And then for the value of lambda, that's just a simple matter of plugging in your estimate for B and your estimate for D, and we get 4.31 for the answer there. So you'll see that there was a bit of information that was a bit of a red herring. We had information on the number of eggs per nest and the percentage that hatched. Just because a chick hatched doesn't mean it's going to survive the first year, and that's the number that you actually want. So if you didn't have information on the average number of chicks per clutch, then you could potentially work with the information on the number of eggs per nest and the hatch rate. But number of chicks per clutch is giving you better information on how many of the offspring actually survive the first year, and that's the number that you need to calculate, because you're adding, if we go back to the equation, if we go back to one of the equations for exponential growth, so you have the population size next year is equal to the current population size plus the number of births, and there's no mortality term coming into this plus the number of births. So this definition has to include the chance that those chicks survive the first year. So now the questions that we want to answer are, what if the population grows exponentially? How many pheasants will there be in 1940? How many pheasants will there be in 1942? And then I just want you to think about the formulas that I have above. So all of the formulas above are exactly the same. Which one is more useful and which is easier to understand? So you can work with any of these formulas, but they're not all going to be as easy to work with. So you want to figure out which one is the easiest to work with. That kind of explains why we derive that formula. That formula is not the easiest one to understand, and that's why we see the other formulas in class 2. So just think about the formulas and which one you like the most. So we'll pause the video here and let you do those calculations. So unpause the video, and one thing you'll see is that, I'm sure you know this about exponential growth by now, but the population gets big really fast once it gets going. I mean, it started off at 10, and then I think there were 35 the next year. Now we're seeing really, really fast growth now that the number of individuals in the population is larger and that each of them has the same per capita reproductive rate and death rate. These are some questions that might show up on the final exam or could show up on homework, and I think these are good things to think about to see if you can actually answer these questions. They involve manipulating the formula a little bit. So find the value of time when the population size is equal to 1,000. For what values of the finite growth rate, lambda, does the population decrease? What happens when lambda equals 1? If we define a quantity td to be the time when the population has doubled its size from what it was at time t, this means that n at td is equal to 2 times n of t. I want you to derive an expression for td, so this is a formula for the doubling time as a function of the current time. And when will the population size have doubled from its size in 1939? So again, those are just to think about. We're not going to do them now.